Hi everyone, I'm Fei Xia from Stanford University. Today I would like to introduce our work on Interactive Gibson, a simulator for embodied visual agents. Interactive Gibson Environments is led by Fei and Silvio, and it is a large team effort involving many students at SVL. We hope to provide a simulation environment that could benefit our research projects as well as a broader community. So what is iGibson? Let me first briefly introduce what it is, and then I will explain the backgrounds and dive into details. First of all, iGibson is a virtual environment where we simulate a robotic agent, for example, a fetch robot in this slide. And we render the virtual images of the environment to simulate sensors of the robot. And the robot is immersed in many of such large environments, reconstructed from real houses. We also simulate realistic physics, so the robot can freely interact with objects in this scene. To give you some quantitative numbers of how large is iGibson, so iGibson has a large dataset of real-world reconstructed buildings. We have 572 buildings, which is 1,400 floors. So we are in the process of annotating in these environments to become fully interactive. So currently we have 10 partially interactive environments and 1 fully interactive environments. As we annotate these environments, we will make them available to a broader community. Secondly, iGibson provides physically realistic simulations of active agents. We have 14 types of active agents. Some of them correspond to real robots. Thirdly, this is very much work in progress. We want to simulate realistically fully interactive environments where you can interact with any object in the scene. So we want it to follow the real world distribution and also the material properties and physics properties. We also want those to be realistic. So why do we want to take such a huge endeavor to build simulation environments? This is inspired by James J. Gibson, after whom our simulation environment Gibson was named. He was an American psychologist that defended the idea that perception is an active process performed by embodied agents in their ecological environments. This was in contrast with a common view at the time of perception as a passive signal processing paradigm. So indeed, we do not want to ask what's inside the head, we want to ask what your head is inside of. So that's why we want to build such an ecological environment, Gibson. Our goal is to create an interactive environment where a robotic agent can perform interactive tasks, just like human. As a first step towards our goal, we created Gibson V1. Just to provide a recap for Gibson V1, it is an embodied navigation agent simulation environment that is mainly geared towards robot navigation. The well-defined task in Gibson V1 is point-to-point navigation. The visuals are rendered with neural rendering, which is realistic but occasionally blurry. The agents in Gibson V1 supported ranges from mobile robots to quadcopters. However, the main limitation is that the mesh is a monolithic piece and doesn't support fine-grained manipulations. Thus, the task we can define in this environment is rather limited. However, as we provide a large database of 3D reconstructed environments, the sheer scale and fidelity fueled a lot of creative works in the computer vision and the robotics community. Some representative works are shown in this slide. People have been using Gibson V1 to train topological navigation, planning and control for mobile robots and quadcopters. As Gibson V1 comes with many modalities, researchers have discovered that using mid-level representation can not only make the reinforcement learning train faster, but the generalization performance is also better. There are other works that explore navigating completely without map or compass, or navigate only using a sequence of images. Some of these works successfully transfer the policy to real, which is a testimonial of the scale and fidelity of such environments. As we want to explore using Gibson beyond navigation, we feel the need of developing a new environment that addresses the shortcomings of Gibson V1. We need an environment that is both visually realistic and allows free interaction with the environment. So currently on the market, there is no simulator supporting that. That's why we developed iGibson. iGibson is a big system with 3-level hierarchy from assets to tasks. So on the very bottom level, it is composed of different assets, different 3D reconstructions of the environments and annotation on these environments to make them interactable, as well as the CAD models we provide in these environments to make them interactable. On the middle level, it's a simulation engine, which include the physics engine to simulate the interactions, and also a rendering engine that can render different modalities of visuals. On the top level is the tasks, definition, and benchmarks. So currently we have navigation tasks, interactive navigation tasks, such as like going through a door. We will include more tasks in the future. And also we have a robot learning infrastructure. Basically, we model all the robots and can simulate all the sensors. Now let's dive deeper into iGibson. Let me highlight some important features that we are able to achieve in iGibson. These features include physics realism, visual quality, ecological distribution of environments, and speed and efficiency. So first, it's about physics realism. Previously, we cannot interact with the environment, so the robot will basically glide into the mesh and slide, which is not very realistic. Now, if the robot runs into a chair, the chair will move with the robot, as would happen in the real life. We can also use the robot itself to push objects to simulate such type of non-prehensile manipulations. And we can also use a robot to open doors, which can facilitate the robot to go from one room to another room. In the iGibson project, we always prioritize high visual quality. For the 3D reconstructions of the environment, the qualities are high because they are reconstructed from the real environments. When we replace objects with CAD models, and when we replace the entire scene with CAD models, we also want to highlight the visual quality. We use a combination of ray tracing based texture baking and real-time rendering to make the visual quality high. Because the fully interactive environments are defined after 3D reconstructed environments, they follow the same object distribution. So you will likely to find a tower near a kitchen counter. So we think this type of distribution is very important for learning important skills for robotic agents. Finally, we still want iGibson to render very fast. So our rendering engine is actually very efficient. It can render frame up to 1,000 frames per second. This will accelerate robot learning. So previously it would take days, weeks. Now it could just take hours or overnight. In this version, we include a cleaned environment with fully interactive sets of objects. We want to scale this up and release more of such environment. This will be our next step. As a summary, I presented iGibson, a state-of-the-art simulator to train robots for visual motor tasks, navigation, and manipulation. iGibson includes hundreds of models of real-world large environments with interactive objects, and it enables easier sim-to-real transfer of learned strategy thanks to realistic virtual images it generates. We are always improving iGibson, so we welcome researchers around the world to check it out. To check it out, you can download and try iGibson from GitHub. The simulator is open source and free. The community is growing rapidly, and we are happy to help you to use it in your research. We have made the installation process easier, so currently you only need to run one pip command. The pip command will download the environment to your computer and start demos. There is one demo that will use the reconstructed environment, and there's another demo that will use the fully interactive environment. Please check it out. Thank you.